Hello, everybody. Today we are going to be going through the implementation of the Translation2d. To give some more insight into what this is, as we did in last video where we kind of motivated it, this is an implementation by WPI library, and we're going to be essentially implementing the logic ourselves. So let's go through the docs really quickly about what this all is about. So again, this is in order to represent geometry in the code. And so what we're going to be focusing on is, so there's translation, rotation, and pose. So translation, as you may understand, it's translating in the X and Y plane. And this is 2 dimensions, so we have X and Y. They also have a Translation3d object where it's X, Y, and Z, but we're focusing on the X and Y right now. So translation in 2 dimensions is represented by the Translation2d class. This class has an X and Y component. Okay, so already I'm seeing that some internal state is X and Y. Okay, so that represents the point X, Y, or this vector on a 2-dimensional coordinate system. You can get the distance to another Translation2d object by using the getDistance method. So I guess this is a function that's defined, or a method that's defined on the Translation2d class, and it returns the distance. Okay, I'm not sure, but okay, so it returns the distance using Pythagorean theorem. Not sure why they just mentioned that one, but okay. Let's see. Then they just go over rotation. Okay, so I guess that's all it is, right? So essentially, we're representing the points X and Y kind of as an object, and we're going to have different methods that we can perform on this. So going back to the code here, I have over here on the right a list of different tests. So there's a get distance, which I guess we'll be going through, and so on. So the first one we're going to work on, and this is called test-driven development. So test-driven development is the idea that you write tests, and what you do is, if I whoa, what just happened? Sorry. You write tests, and where's the getX? Let's re-enable this. And the idea is that you write a test such that it fails, right? It fails, and what you're doing is you are asserting that a certain function is what you expect it to be. So it's an assertion statement. So let's look at this. Hold on, let's just check. Yeah, that's fine. So let's just also, okay, and then I'm gonna put the camera over here just because we don't need that. Okay. So what we're doing here is we're creating an object called T1, and it's of type Translation2d. Okay, so what this first line is doing is it is creating a new object of type Translation2d. So going back here, right, the Translation2d is the class, and we're creating an object which is an instance of this class. Okay, so maybe what I should do is, okay, so what we're doing here is we're creating a Translation2d object where we're passing in the values, the X and Y values that we care about. So what happens is when you call this is called the constructor. And what you're doing here is you're constructing a Translation2d object with the X and Y components equal to the ones provided to us. So as we stated earlier, what you have in a class is two different components. You have the private variables, or the properties, and then you have the methods, or the functions that perform some sort of logic. And this, you'll see that you'll see that the name of this function, Translation2d, is the same as this class. And this is a very special function which is called a constructor. And what a constructor is it's called automatically when you create a new instance. So right when you call this new Translate2d, you run this function. So the first thing we want to do is we want to memorize or hold on to what these two values are. Because after you finish executing what's in between these two curly braces, which is the logic, this x and y value go away. And so this brings us to our first detour, which is data types. Okay, so in Java, when you want to remember or hold some information, this is called, you hold it inside of a bucket, which is called a variable. Okay, and for our purposes, really there's three different main data types. One is an integer, or int for short. One is a double, and one is a Boolean. So an integer is a number that is an integer value, which means that it's a counting number, 1, 2, 3, and it can also be negative numbers, -10, for instance. So it cannot hold decimals. Whereas a double is a little bit bigger of a data type, where you can hold decimals, so 1.1, -1.5, and so on. And if you want to do something in terms of like an if statement, is something true or is something false, that's called a Boolean. So these are the three primitive data types that we care about right now. So let's go back to WPILib. And when we call this constructor, what we're passing in, this x value, is a double, so it can be a decimal point. So what we need to do is we need to hold on to, this is our memory. So what do we care about for the Translation2d? It's going to be a double type, and it's going to be an x, we're going to call it m_x. And just by, you can call it whatever you want. You don't have to do it m_, but just to signify that it's a private variable, we're going to call it m_. So we care about holding on to two properties, m_x and m_y. So what we want to do in here is we want to assign the value of x to this mx value. So you do that by going mx is going to be equal to x. And you do the same thing, my is equal to y. And so after this is run, you now have access to this mx and my value whenever you want. So the first test, again, so now we hold on to, let's go back here to get x. So we've now held on to the x value and the y value. And now what we want to do is when we call this getX function, we want to return the x component of the translation. So how do we do that? Well, again, we've stored it in this mx value, so all we have to do is go mx, and let's check to make sure that it passes. And it does, so that works. So now we're going to do the same thing for get y. So I'm just going to re-enable this test, and it's going to start to be difficult at first, but it's going to start to get easier. So the get y function should just return m_y. And so this leads me to the second topic, which is let's look at this syntax right here. So for now, ignore the public. You see the get y is the name of the function. So if you want to call this function, you reference it by getY. As you see over here, you do t1 dot, and then if you go here, dot, you'll see all of the different functions that are available to you, and we select the getY. Okay, so, but what you see in front of this is you see a data type, and this is what we're returning. So we're returning a double. So my is a double, so you just have to make sure that these match. Okay, so now let's go and see that getY passes. So these are the two very basic ones. Now let's actually do the, I think there's a get distance. Okay, so we are gonna now do the get distance function, which essentially what it does is, actually if we go back over here in the docs, the WPI lib docs, it says you can get the distance to another Translation2d object by using the get distance function, and it uses under the hood Pythagorean theorem. So essentially, right, you have 2 points. I can quickly draw this out. Let's say you have 2 points right here. So in order to get the distance between them, you can actually decompose that into an x component and a y component. Now you have a right triangle, and that's where the Pythagorean theorem comes from. So this, I think I have it over here, yep. So you have a squared, which is, let's say, the x, the y squared, which is the y, and the c squared, which is the distance that you care about. So by doing square root to both sides, you see that c is equal to the square root of this. So how do we actually implement this functionality? Let's make it fail, which it does, good. Now let's go into the get distance implementation. And so I'm using shortcuts for everything, but what you can do is you can right click on this and go to definition, and it jumps to the definition. And so you'll see here that if we go back for a second, we're calling t1 dot get distance. So from get distance's point of view, it knows about the x and y value of t1. But this requires my t1's coordinates and t2's coordinates. And you see that in the parentheses, it's passed in as a parameter. So if we go to the implementation, we're passing in the other point, or xy, as other. So how would we do this? We need to use, let's go over here. So it calculates the distance between two translations in 2D space. Oh, so it actually has the Pythagorean formula here. So what we see is that we need to take the difference in the x's, square it, the difference in the y's and square it, and square root the whole thing. So let's get started on that. So the distance, so I'm going to call the variable which holds difference in x, I'm going to say it's called dx. Okay, and the same for dy. So dx, again, what property type is it? So if we go back here, we have an integer, a double, or a Boolean. So we have the x's are actually doubles, right? The x is a double. So the dx, or the difference in the x, should also be a double. So again, to clarify, the name of the variable is dx, and right in front of any variable that you declare or that you create, or a function which you create, you always have to have the return type. So double dx is equal to, and then it's just going to be the difference in x values. So I'm going to get my x value by mx. I'm going to subtract from that the x value of the other. So you just do other dot, and remember we actually created a function earlier called getx, which just spits out the x value, but this is the x value of the other point. So this is dx. So I do the same for dy. Okay. Okay. So now I have dx and dy. And now the next thing I have to do is square them. So there's two ways of squaring them. So I'm going to create another variable called, let's say, dx2 for dx squared. So there's two ways of doing it. So, I mean, really squaring is just multiplying something by 2. Multiplying something by itself. So you can just do dx times dx. Alternatively, you can actually, there is pre-built functionality that is provided to you. For example, when it comes to mathematics. So if you do math dot, there's a bunch of library methods you can see here. Actually, you just do math dot, you can see all of the different functions that are pre-built in for you. So you have like trigonometry functions here, you have absolute, you know, to get the absolute value, cosine, floor. And what's very important is this pow. So this stands for power, and is there, no, there's no description there. So essentially what this is, hold on. So you have this is your base. So this is like, we want to do dx to the power of 2. In order to do that, you do dx, and then the second parameter is the exponent, so it's 2. So you can do this as well. So dy2 is equal to, and I'm going to do this dy times dy. So I'm going to do it both ways. Once I have the difference of the squares, all I have to do is add them together and then square root it. So how do we square root it? Again, we're going to pull in the math library and do square root. And now it's just dx2 plus dy2. And again, if you don't know that you can do square root like this, all you have to do is you just go into Google and type in Java square root. And the first thing is that it says that, oh, there's a pre-built method for that. So math.square root, that's easy, or power. So you can always Google everything. And so now if we run this test, we can see that get distance passes. Okay, great. So now we've done the get distance. Let's go like this. We have the get distance, get x, get y. Now let's do the get norm. Okay, so what is a norm? It's kind of weird. Or it's kind of a name, if you've never heard it before, it sounds complicated, but it's actually very simple. So the norm is just the distance from the origin. So if you have the x value and the y value here, let's actually go to Excalibur. If you have a line, if you have a point here on 3, 4, it's just the distance from the origin. So this is actually interesting. Why is that? Because we can do Pythagorean theorem again, right? Where we get the difference and we square it, and we do Pythagorean theorem again. But didn't we just create that? Didn't we just do that function in the get distance? Well, we did. So what we can actually do is, the power of programming comes when you can actually reuse bits of code that you've already used. So my idea is we reuse the get distance with the other point being 0, 0, because the norm is just saying what is the distance of this point to this point. We've already done that. So what we can do is, I think we can just do get distance, yeah. And then what are we going to pass in? We have to pass in a point. So let's do origin. And what type is that? Well, that's a Translation2d type, right? Because that's a point. So we have Translation2d origin is equal to new Translation2d. Okay, so, and then we have to pass in 0, 0. Okay. And so going back to the syntax, because again, it can get confusing, is that, and it's always the same. I want to repeat that it's always the same, where you have a variable origin, and right before it is the type. But now you can see that before we had the types as integers, doubles, or booleans. These are called primitive types, and these are built in. However, if you're creating a variable, in this case called origin, it can be of a custom type. And in this case, the custom type is a Translation2d class. So this is the origin, and we can just return get distance of origin. And so this function here, we're reusing existing logic that we've written in get distance, which is more abstract. So if we do test get norm, we should see that if the x is 3 and the y is 4, we should get 5. That's a 3, 4, 5 triangle. And we do. Perfect. Awesome. Okay, so something else that I want to mention. Let's see, should I do it? No, I'm not going to do that right now. Okay, so what is the next function? So the next function is this plus. And so instead of motivating it, first we want to see that this test fails, which good, it does. And so let's analyze this. Here we have 2 points, right? 2 xy points in their Translation2d. So T1 and T2 are their names. T1 is defined as 1, 2, and T2 is defined as 3, 4. So when you do the T1 dot plus and you pass in a second point, what we're doing is when we mean adding 2 points together, we just go on the x's and we add them together. So 1 and 3 becomes 4. 2 and 4 becomes 6. So now how do we implement this logic? Again, here. It returns the sum of 2 translations in 2D space. So for example, translation of this should be 2D, but of 1, 2.5 and 2 plus 2, 5.5, that should just be 1 plus 2 is 3, and 2.5, and 5.5 is 8. So these are, and then this right here is a translation that you want to add, and it returns a sum of the translations. So what is the data type, right? So this is, the plus is the name of the method, and the data type is a Translation2d, right? Because when you take 2 points, let's say here, when you take 2 points, let's just say they're both here, 2 and 3, and their y's are 1. When you take those and you add them together, you get a third point. So the return type of this add is, maybe we can do this, like that point plus that point is equal to that point, right? So the return type of the add method is going to return a new point. And that's exactly what we see here. Plus is the return type of Translation2d. So all we have to do now is we have to get the coordinates of the new x value and the new y value. So again, they're going to be doubles. So new x and double new y. Okay, so the x value. So I need to take my x value, which is m underscore x, and I want to add to it the other dot and then get x. So I'm taking the two x values, my x value and the other's x value, and I'm adding them together. Similarly, we do that. And so now what we want to do is we want to return a new point, as we mentioned earlier. And again, what do we have to pass into it? We have to pass into it an x value and a y value. And again, when this is created, it's going to assign to its own mx the new x value. That's okay. And so now what we do is if we run this, we see that, oh, the plus, hold on. Hold on. Sorry, I have to, because this is a custom class, I need to tell it what does equals mean. So hold on. So what equals means is if the x values and the y values are the same. So what I would do is mx, if mx is equal to the others get x, then the x values are the same. That's great. And you need the y values to be the same. So my is equal to other dot get y. And this is what it means to have 2 points being equal. And so now when I run it, it should pass. Yep, test plus. So now let's do get or test minus, the same thing. So let's go to, we have T1 and T2. T1 is 1, 2, and T2 is 3, 4. And so when you do a minus, if we go to the definition, it's going to be the same, where you take the x values and you subtract them from one another. So 5 minus 1 is 4, and 4 minus 2 is 2. So this is actually basically the exact same thing as the plus. So I'm going to copy and paste the implementation, right? So let's make sure that the minus, test get minus, test minus, yeah. Let's re-enable that test, run this again. Okay, so it fails, and why does it fail? Well, I just copy and paste it. So the only difference is that we have to change a plus to a minus. Let's check it again. And test minus passes. Times is exactly the same thing, where, for example, Translation2d, if you have a point which is at 2, 2.5, you multiply it by 2. Essentially, multiplying a point by a number or a scalar is essentially just component-wise a multiplying. So the x is multiplied by 2 and the y is multiplied by 2. Again, this is the same exact logic, but with a twist. So I'm going to copy this and paste it here. There's no other in this case because it's just a scalar. And what do I have to do to the x value? I have to multiply it. So, whoa, what's going on? Times scalar. Okay. And let's go to the times. Let's re-enable this test. And we see it pass test times. Yep. So, and you can see how kind of using the tests as a guide is a nice idea. So the division is the exact same thing, where if you take a point and you divide it by a number, you're essentially just taking the x and you're dividing it by this number. So let's copy the same logic as for division. And the only thing that we have to do is divide. Okay, now we have to re-enable the test. Oh, we did. And test division passed. Okay. What's next? We have get angle, which we can't do right now because for good reason. ToString. Why do we have that? Let's get rid of that test. We don't care about that really. Okay, and I guess the next, we don't want to do rotations because that's a little not in the scope of this. So let's do get nearest. Okay, so this is a fun one. So I'm gonna motivate this in the following manner. Hold on. Okay. Okay, so we've created 3 points here. So let's go here and let's say we have 3 points. We have 1 point at 1, 1. So let's call this 1, 1. This is 1, and then we have another point at 1, 2. And then we have a point at 1, 3. Okay. And what we want to do is from the perspective of this circle, which we have a list of other points, or I mean it's a point, but we have other points and we want to see which point is the closest to this one. So, I mean, you can see easily that this point right here is the closest to this one. And why is that? Because if you take a line and you take a line to this guy, this has a distance of 1 and this has a distance of 2. Okay, so basically what you do is you want to find the point with the smallest distance. And that's what we want to do. So let's take a detour for a second to describe what's going on here. So again, H3 get nearest. So I'm going to explain this one, okay? So get nearest, right? So we're creating 3 points, T1, T2, and T3. And what we want to do is we want to find which point is closest to T1. Is it T2 or T3? And so the way to do it is, this is another, up until now, we have only been dealing with data types of int, double, or boolean. But what happens if you have a list of 10 of them? So what you can do is you have T2, T3, and you can have T4, T5, and so on. You can have many different points. So what you can do is another expansion. It's not really a primitive data type, but whatever. So we can have a list of, hold on. So what we can do is we can have a list of other data types. So we can have a list of integers. So really it can be 1 and then 2 and then 3 and then 4 and then 5. Okay. So really if you want to be strict, you can say 1 or 2 or 3, right? This int holds a single value. This double holds a single value. This Boolean holds a single value. But a list you can hold onto many values in a nice data structure such that you can actually in the code like iterate, or you can go and you can see what is the first integer, and then the second and the third and the fourth and the fifth. So this is what's called a list. So what we've done over here is we've created a list of, but what's interesting is remember how the primitive data types are int, double, and Boolean. So we can create a list out of these data types. Well, analogously, we can create a list out of Translation2d objects, or a list of points. And this is the way to do it. A list of, can you see it, please? Great, okay. So you can see a list of these points here. So it's a little confusing, I know, but hopefully this is giving you some sort of motivation and intuition to see that it's not actually so confusing if it's explained. Okay, so let's go back to our get nearest. So again, what we want to do is we have a list of points, and we want to check the distance from the point, well, T2, and then from T3, and we want to check its distance to T1. So how do we do that? So this is where we're going to introduce another concept. So again, the description of nearest is it should return the nearest Translation2d, or the nearest point, from a list of translations. So passed into here, we're given a list of translations. And what we should return, remember, right before the name of the function is the data type. So we're returning a point, a Translation2d object. And so now how do we do this? Well, give me just 1 second, please. To print, no, to string. Disregard this, but it's needed. So, okay. So we're doing the get nearest, right? So what we want to do is, as one of the members said in the call, is we want to, okay, so what did we do here? What we did is we went through every point in the list and checked its distance from T1, right? So we went through every point in this list and we checked how far it is from T1. Then what we have to do is we have to save the shortest distance. And so we have to save the shortest distance, and then we want to return that point which is the shortest, from T1. Okay, so let's take this step by step. 1 second. Okay, so we're recording again. Okay, so let's go to nearest. Okay, perfect. So what we want to do is we want to take this step by step. And the first question is, how do we go through every point in the list, or every Translation2d object? Well, there's many ways of doing it, but the way that I'm going to show you right now is what we call a for loop. And let's actually just go for loop Java. Let's look at what this is. So a for loop is something that you can write which executes some bit of code for each item, or so for in our case, we have a list of Translation2d objects, and so we want to run certain logic for every single item. And that's what we're gonna do. And let's actually just, before we enter that, I'm just gonna show you how to do it, kind of. Okay. So the way that you write a for loop is you write for and then parentheses. And this is, the question is, what do we want to loop through? We want to loop through each of these translations. So how we do that is, this might seem a little weird, but what this is saying is, this is, I'm gonna go through each item of translations, and I'm gonna pick out a single one of those points. So, and that's a Translation2d. So again, because this is the first time we're doing it, let's say you have 1, 2, 3, 4, 5. What we're gonna do is, this for loop is gonna start with this 1, and that's like this point here. And then what we do is we go to the second one, and this point will be the second item. And then we go to the third item. This point is that third item in the list. We go to the fourth and the fifth. And then once we've reached the end, then we terminate. We don't do any more because there's no more items in the list. Okay. And so what we're gonna do to see that this is indeed the case is, we're actually gonna print out this point. So, and so now let's actually see if we run the test. Again, we're gonna disable the test, and we're gonna run it, and we should see that it's picking up the point 1, 2 and point 1, 3. And that's exactly what it's doing. So what we're doing is we're picking off the first point that we've set, and then we're printing it out to the screen. And here you can see Translation2d has an x value of 1 and a y value of 2. And then it's going to the next item in the list. Remember, if you go down here, it's 1, 3, and it's printing that to the screen. So what it's doing is it's running this code for every single point in the list. And that's the idea of a list. It's that you can iterate on, you can iterate through a bunch of different objects and do something to every one of them. So now that we're considering every point, now what we need to do is we need to get the distance to that point from T1. So again, T1 can be accessed via MX and MY, but what we want to do is we want to get the distance. We want to get the distance from myself, which is T1, to this new point. And so what we can do is we actually already have the tool in place for that. or we have the function already built for that. So we're gonna get the distance. The distance is a double, right? It can be 1.2 or 0.5 or something. And we already wrote a get distance function, right? And what does the get distance function take in? It takes in another point. Well, that's great because look, we have a point right here. So we don't have to do anything else. We can just call this get distance formula. So now if we just print out the distance, what should we see in this nearest? So if I'm 1, 1, 2 is 1 unit away. So we should see a distance of 1. Translation2d is a distance of 1. Translation2d of this point is a distance of 2. So we are getting the correct distance. So now what we want to do is so we did this comment. We went through every point in the list and we checked its distance from T1. Now what we need to do is we have to save the shortest distance. So I'm gonna call double shortest distance, okay? And this is where I'm not exactly sure what the best way in Java to do this is, but I'm gonna do it in this way. I'm gonna say set it to a huge number, so 1E9. That's 1 with 9 zeros. Okay, so the reason for that is that I just need this to be some sort of a dummy value that will be overridden. Okay? And so why I'm doing that is the following. So what I want to do is now here I have to check. So there's two possibilities, right? So what are the possibilities? My distance is the shortest, is the shortest that has been seen. And the other possibility is another point was shorter than me. Right, so in this case, when the first point is found, a distance of 1 is the shortest distance that's been found. Then if I go over here and I'm analyzing this point, I already found a distance of 1 from a previous point, and I'm not doing any better. So what I have to do is I have to compare my distance. So how do I do this? I have to compare my distance to the distances previously seen. Okay, so how do I do that? So I have to do what's known as an if statement. And so if statement Java. So this is something called a conditional statement, where you can assert some sort of condition. So in this case, we're going to check to see if my distance is the shortest that's been seen. So how do I do that? So I write if, and then inside of these parentheses goes the condition that I care about. So in this case, what is my distance? Well, that's just defined over here. So if distance is shorter, so is smaller. So smaller is just like in math, a smaller angle bracket. And then if my distance is shorter, than the distances previously seen. Well, my shortest distance, I'm carrying this up here as a variable. So I'm just going to say shortest distance. So what this is saying is if my distance is shorter than the distance that you've already seen, I execute the code that's within these angle bracket or these curly braces. And what is the code? Well, I want to update the shortest distance to be equal to my distance, so that I'm holding on to this variable here is holding on to the shortest distance that's seen. So what I can actually do is I can print out the shortest distance. And so what we should see in this case is 1. That is the shortest distance. If I want to create another object called T4, and let's say I want to do it at 1.5. So I have a point that's now super close to this point here, T1. It's only 0.5 away. Well, if I add it to the list, T4, you can see that the shortest distance is 0.5. And it doesn't even matter where I put this in the array, because it'll only it'll only update the shortest distance if there's a shorter distance that's found. So you can see we'll still get 0.5. So now, but 0.5, or this shortest distance, is not actually what we care about. We care about the point that has that is closest. So we don't care about the shortest distance. That's just to check this this condition, if it's shorter or not. But what we care about is we want to, just like this is holding onto some information while going through the loop, we want to hold on to the point. So this is the shortest, or the nearest point. Okay, so we're just going to hold on to the nearest point, and this is going to be of type, remember this is a point, so what goes before it is Translation2d. And we just want to create, just like 1e9 is a dummy value that'll be overridden, we are just going to create new Translation2d. And I don't know, 1e9, 1e9. So it's a point way out in infinity somewhere. And so what we want to do is, if we found a distance that's shorter, we also want to hold on to that point. So we're going to update nearest point to be equal to my point. And so by the end, if I also console log this, the nearest point, you'll see that it actually is returning the point that we care about. So instead of returning just a random value, we just return nearest point. And now if we run this test, oh, it fails, I think, because I added that point. Yeah, okay, so in this case, right, what this assertion is saying is the nearest point in this list to T1 is T2. Well, that's actually not the case, it's T4. So if we run this, we will see that it works. And so what is unary on this? how long is the video? 54 minutes. We'll stop here. This is kind of a weird one. I'm not sure why we would actually need it, but it's very simple to do. And get angle, we're not dealing with angles or rotations. So that wraps up the implementation of the Translation2d. I think where we're going to be going with in the next few, so now we've actually implemented the WPI lib's implementation of Translation2d. Kind of cool is we can actually look at how WPI lib implemented these, and it's very similar. So let's actually do that in the next minute, or in the next few minutes, because it's pretty cool. So, and part of what I want to impart on you is that there's not really black magic going on once you understand what's actually happening. So don't mind this. Okay. So in the so on the right hand side is the constructor. So let's look. So they actually have mx and my also as member variables, and they actually named it the same. That's kind of cool. So this is something that I didn't want to get into really, because it's just, you know, whatever. But if you look over here, this is exactly the implementation that we have. Just ignore these @ signs. That's kind of like metadata and kind of like extra, but it's fluff. It's not really the implementation. So they actually just, our implementation of the constructor is exactly the same as theirs. And let's go to the get distance. So what we did in our get distance is we did math.square root, and we did all of this Pythagorean theorem implementation, and let's see how they did it. So I guess they do a subtraction, and they actually called upon, I guess there's another method in the math library called hypotenuse, and it does Pythagorean theorem for you. So that's how they did it, but you can see how it's identical. Get x and get y, the same thing, right? They're just exposing it. So we actually did exactly what First Robotics, how they implemented it. Again, get norm, we reuse the get distance, which is definitely one way to do it. And they just called math.hypotenuse, which is fine. Same thing, it's still Pythagorean theorem. Get angle, we skipped over that. Rotate by, we skipped over that. Plus, so our implementation of plus is we returned a new translation object where we created a new variable where we just added mx and other.getx. And what did they do? They did the same thing. So they didn't create an extra variable. I agree, it's a little bit wasteful to do that, but whatever, this is for teaching purposes. And then they actually called, so what you can do is you can actually call or access the value of the other's x property directly, but it's safer to do it through this method get x. So, but it's the same exact thing. Minus, same exact thing. Unary minus, I guess it's, you know, we skipped over it. The times, we multiplied by the scalar, same thing. Division, we divided by a scalar, but same thing. And then for the nearest, right? So they actually reused a function, or kind of like a built-in method called collections.min. So Java collection min. One second. So they actually used, I guess, a built-in method called collections.min, but it's under the hood. It's essentially doing the same thing, and that's it. So we see here how our implementation is very similar to how WPILib does it. So where we're going to go next, I believe, is, so we motivated everything from the perspective of Swerve Drive, right? We started over here with Swerve Drive and how Translation2d is actually relevant for Swerve Drive, and here's the code. And then we looked over here. I think what we're going to try to get to is we're going to actually run in simulation some Swerve Drive code. We'll be able to see it we'll actually be able to see it in kind of an on your computer. So I don't know if you can see, but we'll be able to see the Translation2d objects in effect over here. So I think that's what we're going to get to. But thank you so much, and thanks for watching.